Hello, calculus fans! What you see here is called a contour map. This measures the elevation in some region along lines which have the same elevation. So, these are level curves of some function that gives the elevation at any given point in the region. We're going to be thinking about maps like this as we go along. So we're going to say that we have a contour map of elevation e of xy for some fictional location. The level curves join locations with the same elevation. The partial derivative e sub x at some location is the rate of change of elevation with respect to distance if we travel east from that spot. So if you're standing somewhere and you start walking east, you will either slope up or slope down, and then whatever that slope is, that's what the partial derivative is. E sub y is the rate of change of elevation when we travel north. So east and north because that's the positive x and the positive y axis if we superimpose a coordinate system on this map. What if we want to travel southwest or some other direction? There still could be some rate of change associated with that kind of movement. So we're going to introduce a new type of derivative, which is called a directional derivative. That's going to let us find the rate of change of some function of two or more variables in any direction. Up to this point, we've been restricted to computing partial derivatives where our direction of motion is specifically in the x direction and the y direction. Now remember how we defined the partial derivatives fx and fy of a function z. They're defined as limits, and here are the limits that we used. These represent the rates of change of the function z in the x and y directions. If you like, they represent rates of change in the direction of the unit vectors I and j. Let's say that now we want to find the rate of change of z at some point x naught, y naught in the direction of an arbitrary unit vector u with components a, b. Let's take the surface that has equation z equals f of x, y. So that's the graph of f. And we'll let z naught be equal to f of x naught, y naught. So that's the z coordinate of the point on the surface. Now we have a point P, x naught, y naught, z naught on the surface. And then we'll take a vertical plane that passes through the point P in the direction of the unit vector u, and that's going to intersect our surface in a curve. Now we've done this before with the partial derivatives, except that the plane that we used to intersect was parallel to the coordinate axes. This time it's not parallel to the coordinate axes, it's going to be parallel to some unit vector u. The slope of the tangent line t to the curve at the point P is going to be the rate of change of our function in the direction of u. Now let's suppose we have another point on the curve C. This is just some arbitrary point x, y, z. And we'll project into the xy plane. We'll take P and Q and project them into the xy plane. And we get the points P prime and Q prime. So that means the vector P prime Q prime is parallel to u. So we can say that P prime Q prime is equal to h times the vector u for some scalar h. So we'll say that x minus x naught is equal to ha, y minus y naught is equal to hb. And then if we rearrange, we'll get x is equal to x naught plus ha, y equals y naught plus hb. And so now, if we take the change in z over h, we get this expression, f of x naught plus ha, y naught plus hb, minus f of x naught, y naught all over h. Let's take a limit of this as h goes to 0. And what we get now is the rate of change of z with respect to distance in the direction of u. And that's called the directional derivative of f in the direction of u. So as a definition, we're going to say this. The notation that we're going to use for directional derivative, we're going to use a capital D for directional derivative, and then a subscript of the unit vector, and then whatever function we're dealing with, and then the coordinates of the point at which we're evaluating the directional derivative. And it's equal to this limit, assuming that this limit exists. Now we don't want to compute limits every time we want to do a directional derivative, so we're going to give a nice computational formula for computing this. Then we can avoid computing limits. So the theorem says that if f is a differentiable function of x and y, and remember that that means that a tangent plane will approximate the function when you're near the point, then f has a directional derivative in the direction of any unit vector ab, and here's a formula that computes the directional derivative of f in the direction of u at the point xy. It's the partial derivative with respect to x at xy times a plus the partial derivative with respect to y at xy times b. Okay, that's all for now.